In section 9.1, we're going to start talking about functions of several variables. And what that means is functions whose input is not just an x, but more variables than that. We'll start with functions of two variables. And here's an example of why we might want to do this. Think about the Earth and the temperature on the surface of the Earth. So the temperature T at any point on the surface of the Earth can be thought of as a function basically of where you are. To be specific, as a function of latitude and longitude. So let's let x be the variable that represents the latitude. And let's let y be the variable that represents the longitude. So to express this, we say t is a function of x and y. So I'm going to write t equals t of x and y. This looks kind of funny, but it's a really common math way of saying this output variable t happens to be a function of x and y. And this thing here, you would read t is a function of x and y. Now, I think our textbook tends to use a different letter, so it'll say t is a function of x and y like that, which is fine. And I think the reason the textbook does that is just to emphasize that t is an output of some function. But honestly, it's probably more common to just say t equals t of x and y. So just so you're familiar with both of those ways of writing things down. So to be a little more precise about what we mean by this, a function of two variables is a rule that assigns to each ordered pair of real numbers. So ordered pairs of real numbers, we're typically used to calling those x and y. Obviously, you could use other letters, but let's stick with x and y for now. So the x's and y's in some set D that we call the domain, a unique real number denoted f of xy, or whatever letters you're using in your particular example. The range of f is the set of values that takes on. In other words, it's the set of all the outputs of the function. Now, how should we picture something like this? Well, let's go back to the familiar old function of one variable. Where our inputs are just single real numbers, x's, and let's say our domain is that interval on the x-axis, going from there to there. The graph you'll get by taking the output of your function for each x value, and maybe they do something like this, and then you hopefully can see enough of a pattern to connect the dots, because we can't possibly graph every infinite number of dots. And we think of the output, so at any given y value here, the output, we represent by putting that point a certain height above the x-axis. Now, what's going on with functions of two variables is our inputs are on the xy plane, because there's two variables for every input. So let's say our domain happened to be this region in the xy plane. Once again, we're going to well, let me do a little bit of labeling here. So in the function of one variable, we have y equals f of x. In the function of two variables, we have our output, which we'll often call z, is a function of both x and y. But you can still think of that output as a height. So if I were to take all my xy points and in the domain and then use the output of f as the height above that, then what I'm going to get is some sort of surface. So just kind of for sake of example, there will be some sort of surface floating above or below the xy plane where the output that we're calling z is represented by putting a point that's that height above the xy point in the domain. So again, for a familiar function of one variable, the graph is going to be a curve. For this new business function of two variables, the graph is going to be some kind of surface in 3 dimensions. So curve in 2 dimensions, surface in 3 dimensions. And before I forget, 2D is often represented with an R, capital R with a double leg and a superscript 2. 3 dimensions is often represented as the capital R with a double leg and a superscript 3. Okay, hopefully that gives you some idea of what's going on here.